Hello and welcome. In this tutorial, you will learn how to detect anomalies in images. For this, we use MVTec HALCON's deep learning-based global context anomaly detection. For a general introduction to this technology, please refer to the linked video. In HDevelop, MVTec provides a workflow example. This example leads us through the workflow, from data preparation to training, evaluation, and inference. The last part is specific to global context anomaly detection and shows some results of the local and global network. Let's go through the example step by step. By default, the example uses a model that has been trained by MVTec. Set this parameter to false to enable the training of your own model. Now, we start the first step of the workflow. First, the images are preprocessed. Then the preprocessed images are displayed. Since the global context anomaly detection model requires a lot of memory, we need to reduce the image size. However, the anomalies still need to be visible in the images. The parameter patch size is specific to global context anomaly detection. The default works for many use cases. If you want to adapt it, have a look at the documentation of getDL model param. Additionally, it can be helpful to align the images such that the orientation of your objects varies as little as possible. By removing this variety, you can make the job of the global network easier. Cropping the images is also helpful to reduce clutter and maximize the resolution of important information. Next, we train the model. Here, the training takes about an hour. To speed up the training, the number of training steps can be reduced to see whether an application works in principle. However, for the final application, we recommend training the model with at least the default number of 70,000 training steps. The global network in particular also profits from augmenting the image data. Again, the defaults are a good starting point and good for many use cases. Let's watch the training progress sped up. After training, it's important to normalize the anomaly scores of the local and the global networks to the same scale. This is necessary for the next step after training. When the training is finished, we evaluate the trained model. Here we compute two types of thresholds to make the following decisions. When applying the trained model, we get a DL result dictionary containing an anomaly image and an anomaly score. In the anomaly image, we need a threshold to decide which pixels represent an anomaly. We call this the anomaly segmentation threshold. When applying this threshold, we get an anomaly region. For the anomaly score, we need a threshold to decide whether the image is classified as containing an anomaly. We call this the anomaly classification threshold. When applying this threshold, the anomaly class is either OK or not OK. Both parameters can be calculated with the procedure compute DL anomaly thresholds. If you provide both good and bad samples, the anomaly classification thresholds comprises three thresholds. Consider this visualization. You can see anomaly scores on the x-axis and the fraction of wrongly classified images for a given anomaly classification threshold on the y-axis. The first threshold, in blue, represents the threshold where there would be no wrongly classified OK images. The second threshold, in red, represents the threshold where there would be no wrongly classified not OK images. Finally, the black threshold represents the threshold where the sum of false results is minimal. Note that the blue and the black threshold are identical in this example. Thus, only the black threshold is visible here. In most cases, one of these thresholds is suitable for your application. Or, this being HALCON, you can adapt these values however your application requires it. With these parameters set, we can visualize the evaluation on the test split. You can see pie charts on the precision and recall, and a confusion matrix. Lastly, we want to run the inference on some test images. The preprocessing needs to be the same as for the training. Apply DL model returns the anomaly image and an anomaly score. This procedure then applies the thresholds we computed earlier on the image and score. Then we can display the results. On the right side, the anomaly image is displayed as a heat map on top of the original image. On the left side, the red regions indicate areas where the segmentation threshold was exceeded. Based on the anomaly score and the classification threshold, an OK, not OK decision is made. Last, let's see some examples of the results of the local and global network. First, we process some images that showcase logical anomalies. You can see how the global network reacts more strongly here. Then, we display some images with structural anomalies. Here, the local network often reacts stronger. Note that the distinction of logical and structural anomalies often can be ambiguous. Some defects can be considered both logical and structural, like a contamination with another juice. At this point, you might notice that one of the subnetworks would be sufficient for your specific application. Thus, it's possible to train or deploy a model that only uses either one of the networks. This improves the runtime and reduces the required memory. This concludes this video. As you have seen, global context anomaly detection is a powerful technology. Try it out for yourself in this HDevelop example. Thank you for watching.